Welcome. Let me get back to the problem of positive sectional curvature in Q manifolds. Here is the definition of a Q manifold. It's a few lines of definitions, recursive definitions. Essentially means that the unit sphere at every point is a sphere. It's a nice small definition, and we can ask to define curvature in such a framework so that we have the usual manifolds as positive curvature manifolds, and we want also to have a bound, a Myers bound for the size of a manifold if it has positive curvature, and we also want to have a sphere theorem, sufficiently pinched, simply connected manifolds should be spheres. So this is a goal, and we want to do that all in the finite. So I worked on this for quite a few years, and the most naive way how you can define positive curvature is that you have every embedded two-dimensional disk has positive curvature. We have also the notion of Q manifolds within graphs, and this is just completely absorbed in this framework, and what we have can say that every embedded wheel graph which generates the wheel graph has positive curvature, but that's very, very restrictive, as I showed with the Mickey Mouse theorem, which tells that if you have this strong assumption, then every Q manifold is a Q sphere. So, too strong. Index expectation is a nice way. I see this index expectation as actually something which is a numerical scheme. It works, and because you can always take a manifold, you triangulate it, put it in a high dimensional Euclidean space, you get the index expectation. You can use this to define sectional curvature, and then positive sectional curvature really corresponds to that. So this is not really kind of a fundamental. I really would like to have a notion which involves also the geodesic framework, right? We want to have geodesics which define a geodesic sheet, and then the curvature of this geodesic sheet should be the curvature. By the way, all curvatures should have Gauss-Bonnet theorem, otherwise I'm not interested in this curvature. I've tried then kind of just in this winter, starting this winter, is to define, a geodesic flow, which actually is very nice. I think it works. For example, this is a geodesic path, a closed geodesic path, which defines then in a Q manifold a sub-Q manifold with boundary, which has then as a boundary Q-1 manifold. And this was the shock which I actually I defined this kind of in a couple of videos already. I looked at these geodesic sheets, looked at the curvature of these geodesic sheets. You can do that in various ways. So you can take the Ishida-Higuchi curvature, or you can take the curvature which is more based on the bones, and then you get a curvature which is here, and these curvatures work very well. I mean, they give you what you want. But the problem was, and that was a shock of mid-April, I talked about this, was to realize that these manifolds, these sphere bundles, which we have defined like that as boundaries of geodesic, closed geodesics, they have positive curvature with this definition. It's definitely not good, because all this fails, right? We don't have a finite diameter. This can be made arbitrarily large, right? N can be arbitrarily large, so you have arbitrarily large manifolds with the same curvature. The lowest value of the curvature doesn't depend on N, and you also don't have the known positive curvature manifolds, because these are, for example, S1 cross SQ minus 1, which is a generalized torus type, which is not a sphere. We also don't have the sphere theorem. So it's a real disaster for me, and this was I would consider this even a crisis. I was thinking the whole second half of April about this, and it's obvious that you want to kind of define a larger Grassmannian. So the Grassmannian of the the space of two-dimensional planes, that's kind of what you can define here with bones, right? A two-dimensional bone. A two-dimensional bone is just defined by a q minus 2 simplex in the simplicial complex, and that this defines then a two-dimensional plane, discrete version of a two-dimensional plane, which then defines a geodesic sheet. But that was too restrictive, and so I tried to extend this. And one way to extend this is which is actually quite natural, and I like it. It's actually more beautiful even. I take the simplex and I take a triangle in that simplex. If I take a triangle in that simplex, which is 3 points in that simplex, then we can have 3 bones, right? The 3 edges define 3 bones, and the 3 vertices define 3 walls. And so we can define with this, we can then define kind of also something like a local disk embedded in the manifold. And in this case, these are much more. And if you take all the pairs of x and triangles, which is kind of like an element in this Grassmannian, is much larger than just taking the bones. So in this case, still what happens is the curvature is still positive. It's not so surprising, right? If you look at the picture of a product manifold, so this is S1 and this is say S2, for example, what happens is this is then a 3-dimensional space, almost all Grassmannian, or elements of the Grassmannian, almost all planes which you have here have positive curvature, right? You have to have contained S1. So these are almost all planes do not satisfy, have not the property that they contain this S1, and so it's not surprising that in the discrete we kind of miss that S1. So how to do that? We want to define still curvature in such a way, sectional curvature in such a way that positive sectional curvature gives us all these properties. And there's no compromise here. This is really what we want to have. Otherwise it's not good. And so it's obvious that we have to extend the concept of Grassmannian even more. We have to allow more general planes. And what happens here in this case is, and if you look at these manifolds here, arbitrary dimension, what happens is if you look at this, they are tori inside, but they are not made of the geodesic sheets which we have. So what happens, and that's kind of an interesting thing, and that's kind of typical what happens in differential geometry. If you have a point and you move, you have a frame, a local frame, a triangle. When you go here, that triangle moves with it. So this is a moving frame of Cartan, and that triangle here changes. And if you are going here, then you also, with the geodesic, you are moving the frame. So the geodesic parallel transport of the geodesic really moves also the frame. And what happens is when we do that in this way with this fixed frame here, what happens is we get always kind of, we get sheets which have positive curvature. But what happens when you look at it, you can investigate that, which bones have 0 curvature, 6 meaning flat. So they are these generalized manifolds, submanifolds, which are tori inside this manifold, but they are not made directly of geodesic sheets how we define them. What happens is probably, and I have to try that, is when we are looking at neighbors, we have to also allow to change the orientation. So we have to allow more general triangles than the triangles which we have here. And then it would work, right? Because then we would actually have here also sheets. We would also get sheets which are flat, geodesic sheets which are flat. So I have to experiment with this. This video was just to get organized and really knowing what the problem is. That's all for today.